You are about to hear a question that should not exist in serious science. And yet, it does. What if 200 million years ago, long before humans, long before mammals, even before dinosaurs became dominant, Earth was home to a technological civilization? Not primitive, not experimental, but advanced, capable of manipulating materials, energy, and possibly even nuclear processes. If that sounds impossible, stay with me. Because the problem is not the lack of imagination. The problem is the limits of evidence. Before we go deeper, write in the comments where you're watching from. I read them. And if you want more investigations like this, structured, evidence-based, no nonsense, subscribe, like, and stay with this channel. Now, let's establish the scale. Earth is about 4.5 billion years old. All of recorded human history, every empire, every war, every invention, fits into roughly 5,000 years. That is 0.0001% of Earth's timeline. Dinosaurs ruled for about 165 million years. That alone is 33,000 times longer than human civilization. And before them, there were hundreds of millions of years we barely understand. The Triassic period, around 200 million years ago, is usually described as a recovery phase after the largest mass extinction in Earth's history. Around 96% of marine species and 70% of terrestrial vertebrates disappeared. What followed was a planetary reset. New ecosystems formed. New species emerged. Evolution accelerated. At that time, all continents were joined into a single supercontinent, Pangaea. It stretched from pole to pole, surrounded by a global ocean called Panthalassa. Climate conditions were fundamentally different. There were no polar ice caps. Atmospheric CO2 levels were several times higher than today, creating a strong greenhouse effect. Global temperatures were higher, but stable. Large inland deserts existed, but coastal and river regions supported dense vegetation and complex ecosystems. From a purely environmental perspective, these are not hostile conditions. In fact, they are favorable for large-scale biological complexity. Stable climate, abundant resources, wide migration corridors across a unified landmass. These are the same macro conditions that, millions of years later, would support the rise of human civilization. Now the critical question: does intelligence require humans? Modern science assumes that technological intelligence is extremely rare, because we only have one example: us. But statistically, that's a sample size of one. Evolution does not follow a fixed path. It experiments, repeatedly, over hundreds of millions of years. Different environments, different pressures, different biological solutions. The assumption that intelligence emerged only once is not a proven fact. It is an inference based on limited data. And here is where the real problem begins. Even if an advanced civilization existed 200 million years ago, almost all physical evidence of its existence would be gone, completely erased. Geology is not a static archive. It is an active system. Continents move. Ocean floors are recycled through subduction. Mountain ranges rise and erode. Surface materials are buried, compressed, melted, and transformed. Over tens of millions of years, the surface of Earth is rewritten. Less than 1% of the Earth's surface from the Triassic period is still accessible today in a relatively unchanged form. That means over 99% of any structures, cities, or artifacts from that time would have been destroyed or altered beyond recognition. Even our modern cities would not survive this process. Steel corrodes within thousands of years. Concrete fractures and erodes within centuries to millennia. Glass degrades. Plastics break down into microparticles. Within 10,000 years, most of our infrastructure would collapse. Within 1,000,000 years, only chemical traces would remain. Within 100 million years, even those traces would be extremely difficult to identify. This is not speculation. This is established geophysics, which leads to a paradox. If a civilization existed that long ago, we would not expect to find buildings, tools, or obvious artifacts. We would expect anomalies, subtle deviations, chemical signatures, structures that do not fully align with natural processes. And this is exactly where things become complicated. Because despite these limitations, certain anomalies do exist. Objects embedded in ancient rock layers that do not match expected geological formation. Metallic compositions that require high-temperature processing found in contexts where such processes should not occur. Microstructures resembling engineered components. Isotopic signatures that suggest energy processes far beyond natural background levels. Individually, each case can be dismissed. Misinterpretation, contamination, rare geological formation. But collectively, they form a pattern that does not fit cleanly into our current model of Earth's history. In the next part, we move deeper into the Triassic world itself. Not speculation. Data, climate systems, atmospheric chemistry, biological diversity, and whether conditions truly allowed the emergence of something more than just life. To understand whether a technological civilization could have emerged 200 million years ago, we need to remove speculation and look strictly at physical conditions. The Triassic Earth was not primitive in a biological sense. It was transitional, but highly dynamic. The planet had just exited the Permian-Triassic extinction event, the most severe in Earth's history. This event eliminated up to 96% of marine species and reshaped the entire biosphere. What followed was not stagnation, but rapid evolutionary expansion. Empty ecological niches triggered diversification at a global scale. Pangaea played a central role in this process. Unlike today's fragmented continents, Pangaea formed a continuous landmass covering roughly 30% of the Earth's surface. This allowed uninterrupted migration across thousands of kilometers. Species were not geographically isolated in the same way they are today. Genetic exchange, competition, and adaptation occurred across a unified environment. From a systems perspective, this increases evolutionary pressure and accelerates complexity. Climate stability is another critical factor. The Triassic atmosphere contains significantly higher concentrations of carbon dioxide, estimated at 4 to 5 times modern levels. This created a greenhouse climate with minimal temperature gradients between equator and poles. No permanent ice caps. No extreme seasonal freezing. This matters because long-term environmental stability is a key condition for the development of complex systems. Civilizations, biological or technological, require predictability. Volatile climates reset progress. Stable climates allow accumulation. In coastal regions and river basins, ecosystems were dense and resource-rich. Ferns, conifers, and early gymnosperms dominated vegetation. These supported herbivorous species, which in turn supported predators. Food chains were established, diversified, and relatively stable over long periods. Water systems were extensive. Large river networks crossed Pangaea, creating corridors of fertility. These zones would have been optimal for any form of complex life requiring consistent access to water, biomass, and raw materials. Now consider energy availability. Photosynthesis was highly active due to elevated CO2 levels. This increases primary productivity, the base of the food chain. More energy at the base means more energy available for higher-level organisms. In evolutionary terms, this creates the potential for larger brains, more complex behaviors, and eventually intelligence. This is not theoretical. It is observed across multiple evolutionary pathways. However, there is a constraint. The dominant life forms of the Triassic were reptiles, early archosaurs, and amphibians. The first dinosaurs appeared around 230 million years ago, but they were initially small and not dominant. Mammals existed, but only as small nocturnal creatures with limited ecological impact. So the question becomes, could intelligence emerge outside the mammalian lineage? Neuroscience does not require mammals for intelligence. It requires certain structural conditions: centralized nervous systems, sensory integration, memory capacity, and social interaction. These features are not exclusive to mammals. They are evolutionary solutions that can, in theory, emerge in different biological architectures. Cephalopods, like octopuses, demonstrate high intelligence without mammalian brains. Birds show advanced cognition with completely different neural structures. This proves that intelligence is not tied to a single biological template, which means the absence of mammal dominance in the Triassic does not eliminate the possibility of intelligence. It only changes its potential form. Another factor often ignored is time depth. The Triassic period lasted approximately 50 million years. For comparison, human civilization, from early agriculture to modern technology, developed in less than 10,000 years. That is 0.02% of the Triassic time span. Even if intelligence emerged briefly in a localized region and existed for only a fraction of that period, it would still have had enough time to develop advanced systems. The limitation is not time. The limitation is preservation. And preservation, in geological terms, is extremely inefficient. Surface structures are the first to disappear. Organic materials decay rapidly. Metals oxidize. Only under very specific conditions, rapid burial, low oxygen, minimal tectonic disturbance, can artifacts survive long-term. But even then, survival does not mean recognizability. A manufactured object exposed to millions of years of pressure, heat, and chemical alteration may no longer resemble its original form. It may appear as a mineral anomaly, a geometric irregularity, or an unusual chemical concentration. Which leads us to a critical shift in perspective. We should not be asking, where are the cities? We should be asking, what would be left if the cities were gone? Because if a civilization existed in the Triassic, its legacy would not look like ruins. It would look like anomalies. In the next part, we examine the fundamental limitation that defines this entire investigation: the destruction and rewriting of Earth's geological record, and why even the most advanced civilization could vanish almost without a trace. If a technological civilization existed 200 million years ago, the main reason we don't see clear evidence today is not because it never existed. It is because Earth does not preserve surface history well. Geology is a destructive system. The surface of the planet is constantly recycled through processes that operate on timescales far beyond human perception. Plate tectonics alone ensures that large portions of Earth's crust are continuously destroyed and recreated. Oceanic crust, for example, has an average lifespan of less than 200 million years. Anything built on it would have been subducted into the mantle and completely erased. Continental crust survives longer, but it is not stable either. Mountains rise and erode. Sediments accumulate, compact, and transform into rock. Older layers are buried under newer ones. Heat and pressure alter mineral structures through metamorphism. Chemical reactions change composition over time. Even without tectonic recycling, surface features degrade rapidly. Erosion is the first filter. Wind, water, and temperature fluctuations break down structures at all scales. Sharp edges disappear. Surfaces smooth out. Materials fragment. Within thousands of years, most human-made structures begin to lose their defining characteristics. Within tens of thousands, they are indistinguishable from natural formations unless specifically preserved. Now extend that timeline to millions of years, then tens of millions, then hundreds of millions. At 200 million years, the probability of preserving recognizable artifacts approaches zero. This is known in geology as the preservation problem. Even under ideal conditions, preservation is selective. Fossils exist not because life was rare, but because fossilization is rare. Most organisms that ever lived left no trace. The same principle applies to technology. Most artifacts would decay before they could be preserved. Only a tiny fraction, those buried quickly under specific conditions, would survive. And even those would not remain unchanged. Heat and pressure modify structure. Metals can recrystallize. Organic materials carbonize. Complex objects lose detail. Over time, the original function becomes impossible to identify. What remains is not a tool or a machine, but a distorted remnant embedded in rock. From a scientific standpoint, this creates a classification problem. We identify artifacts based on form, composition, and context. But if all three are altered, recognition fails. A manufactured object subjected to geological processes may appear as an unusual mineral inclusion, a geometric irregularity, a concentration of rare elements, a structure that mimics natural patterns. In many cases, these are dismissed as geological anomalies, not because they are proven natural, but because there is no framework to classify them as artificial. This is where scientific bias becomes relevant. Science operates within models. These models define what is considered possible. Any observation that falls outside the model is typically reinterpreted to fit it. This is not corruption. It is methodological necessity. Without stable models, science cannot function. But it creates a limitation. If the current model assumes that technological civilizations only appeared recently, then any evidence suggesting otherwise will be treated as error until proven beyond doubt. And beyond doubt at geological timescales is an extremely high threshold. Now consider another factor: scale of detectability. A modern city occupies a small fraction of Earth's surface. Even at peak industrialization, human infrastructure covers less than 1% of land area. If a past civilization had similar or even larger footprint, it would still represent a tiny signal relative to the entire planet. Combine that with 200 million years of geological transformation, and the signal becomes almost indistinguishable from background noise. Which means detection requires indirect methods. Not ruins, not buildings, but signatures. Long-term indicators that persist beyond physical structures. Isotopic anomalies, unusual element concentrations, non-random geometric formations, material compositions requiring high-energy processes. These are the types of evidence that can survive deep time. And this is exactly the approach proposed by modern scientific frameworks like the Silurian hypothesis, not looking for direct artifacts, but for geological fingerprints of industrial activity. Because if something existed, this is where it would remain. In the next part, we move from theory to method. We examine how scientists attempt to detect civilizations that may have left no visible traces, and what specific signals they consider impossible to produce naturally. Modern science does not directly claim that ancient technological civilizations existed before humans, but it does address a more precise and uncomfortable question. If such a civilization had existed, would we even be able to detect it? This question led to the formulation of what is now known as the Silurian hypothesis. The name originates from a fictional species in a science fiction series, but the scientific framework behind it is entirely real. It was proposed by astrophysicist Adam Frank and climate scientist Gavin Schmidt as a methodological investigation, not as a claim. Their objective was simple: define what evidence an industrial civilization would leave behind over millions of years, and whether that evidence could still be found. Their conclusion was not intuitive. Most direct evidence would not survive. No buildings, no machines, no infrastructure in recognizable form. Instead, the only viable signals would be indirect, embedded in geology, chemistry, and planetary systems. The first category is atmospheric alteration. An industrial civilization changes the composition of its atmosphere. The large-scale combustion of carbon-based fuels increases carbon dioxide and methane levels. These changes can be recorded in geological archives such as sediment layers and isotopic ratios. For example, modern industrial activity has already altered the carbon isotope balance in Earth's atmosphere. The ratio between carbon-12 and carbon-13 has shifted measurably due to fossil fuel combustion. This shift is globally distributed and can be preserved in future geological records. Now extend that logic backward. If a similar shift occurred millions of years ago, it could indicate large-scale carbon release. But there is a complication. Natural processes can produce similar signals. Volcanic activity, methane release from ocean sediments, and large-scale biomass decay can all alter carbon ratios. This creates ambiguity. The signal exists, but interpretation is uncertain. The second category is synthetic materials. Modern civilization produces substances that do not occur naturally, such as plastics and complex alloys. Over time, these materials degrade, but they do not disappear completely. Plastics fragment into microparticles that can be incorporated into sediments. Metals corrode but leave behind trace elements in unusual concentrations. Over millions of years, these materials would not remain intact, but their chemical signatures could persist. However, again, detection is difficult. Microplastics degrade chemically. Metal distributions can be altered by geological processes. Distinguishing between natural and artificial sources becomes increasingly complex with time. The third category is isotopic anomalies. This is one of the most important indicators. Certain isotopes are either extremely rare or entirely absent in natural conditions. For example, some radioactive isotopes are produced primarily through nuclear reactions. If detected in unexpected concentrations, they can indicate high-energy processes. In modern terms, nuclear reactors and weapons produce distinct isotopic signatures, combinations of elements that do not occur naturally in the same ratios. If similar signatures were found in ancient geological layers, they would require explanation. And this is where the hypothesis becomes more precise. Frank and Schmidt identified that even nuclear activity might not leave clear, lasting traces over tens or hundreds of millions of years. Radioactive isotopes decay. Geological processes redistribute elements. Oceanic crust is recycled. The signal weakens over time. In many cases, it disappears entirely. The fourth category is biological impact. A technological civilization can cause rapid environmental change, mass extinctions, climate shifts, biodiversity collapse. These events are preserved in the fossil record as sudden transitions. But again, nature can produce similar effects. Volcanic eruptions, asteroid impacts, and natural climate cycles can also trigger mass extinctions. Without additional evidence, it is impossible to attribute such events to technological causes. This leads to the central limitation of the Silurian hypothesis. No single signal is sufficient. Only a combination of multiple independent anomalies occurring simultaneously could suggest technological activity. And even then, certainty is not guaranteed. Because the deeper we go into geological time, the more incomplete the record becomes. Less than 1% of ocean floor older than 200 million years still exists. Continental records are fragmented. Sedimentary layers are interrupted. Entire regions of Earth's history are missing or compressed into thin strata, which means absence of evidence is not evidence of absence. It simply reflects the limits of preservation. Now, here is the critical implication. It is scientifically possible that an industrial civilization existed hundreds of millions of years ago, and that we would not be able to prove it conclusively with current methods, not because the evidence never existed, but because the planet itself erased most of it. This does not confirm the existence of such a civilization, but it removes the assumption that it is impossible. And once that assumption is removed, the interpretation of anomalies changes. Because now, instead of asking, "This cannot be artificial," we ask a different question. What if we are misclassifying evidence because we are not expecting to find it? In the next part, we move from theory to data. We begin with one of the most controversial categories of anomalies: metallic objects embedded in ancient geological formations that appear to require conditions far beyond natural processes. Among all categories of anomalous findings, metallic objects embedded in ancient geological formations remain one of the most controversial and one of the most difficult to dismiss outright. Because unlike ambiguous chemical signals, metal composition can be measured precisely, and certain compositions should not exist without controlled, high-temperature processes. One of the most frequently cited cases comes from South Africa, where miners have, for decades, reported the discovery of small metallic spheres embedded within Precambrian rock layers. These formations are estimated to be up to 3 billion years old, long before complex life emerged. The objects themselves vary in size, typically between 1 and 10 centimeters in diameter. Some are nearly perfectly spherical, with deviations measured in fractions of a millimeter. Others display parallel grooves, often 3, running around their equator with consistent spacing. From a manufacturing perspective, this level of symmetry is not trivial. Precision spheres require controlled shaping or melting conditions. Parallel grooves with consistent depth and spacing imply intentional structuring. The official geological explanation classifies these objects as concretions, natural mineral formations created through chemical precipitation in sedimentary environments. Concretions can indeed form spherical shapes, but they typically show irregular surfaces, internal layering, and compositional gradients. They do not usually display uniform grooves with consistent geometry across multiple samples. More importantly, Some of these spheres are composed of metallic alloys containing elements such as nickel and iron, in configurations that require specific formation conditions. Natural processes can concentrate metals, but forming structured alloys with uniform distribution at that scale, without melting, without industrial temperatures, remains difficult to explain. A second category of metallic anomalies involves tubular structures found in ancient rock formations. In certain geological surveys, cylindrical metallic objects have been reported embedded in quartzite layers dating back over 2 billion years. These structures exhibit hollow interiors, uniform wall thickness, and linear geometry extending several centimeters to tens of centimeters in length. From an engineering perspective, hollow cylinders with consistent dimensions are functional designs. They suggest flow systems, conduits, or structural components. Geologically, natural tubular formations do exist, such as fossilized burrows or mineral veins. But these typically follow irregular paths, branching patterns, or sedimentary layering. They do not maintain straight alignment across solid rock, nor exhibit uniform internal surfaces. In some reported cases, internal surfaces of these tubes display spiral patterns, resembling thread-like structures. If confirmed, such features would strongly suggest rotational shaping processes, which implies tooling, and tooling implies technology. At this point, the standard counter-argument becomes essential. Contamination. Could these objects have been introduced into the rock at a later stage? This is always the first hypothesis considered in geology. Modern objects can enter cracks, fissures, or mining environments and later appear embedded within rock. However, in multiple reports, these objects were found fully enclosed within solid rock matrices, without visible entry paths or fractures connecting them to the surface. Additionally, the surrounding rock often shows no signs of disturbance. This significantly complicates contamination explanations. The second counter-argument is misinterpretation. Natural geological processes can produce highly regular structures under certain conditions. Crystal growth, pressure gradients, and chemical diffusion can create patterns that mimic artificial geometry. And this is true. Nature can produce symmetry. But there is a threshold where coincidence becomes statistically unlikely, especially when multiple independent features appear together. Precise geometry, consistent dimensions, alloy composition, internal structuring. Individually, each feature can be explained. Combined, they form a pattern that becomes increasingly difficult to attribute purely to natural processes. Still, none of these findings constitute definitive proof, because each case lacks one critical element: context. We do not have associated tools, no clear production sites, no systematic distribution patterns across large areas, no continuous technological layer. Instead, we have isolated anomalies. And isolated anomalies in science remain unresolved, not confirmed. But their existence raises a critical methodological question. At what point does accumulation of anomalies require revision of the model? Because if even a small fraction of these objects are not natural, then they represent evidence of processes that should not exist in the geological timeline we currently accept. And if such processes existed, they must have had a source. In the next part, we move from materials to imprints, fossilized structures that appear to record interaction, pressure, and motion in ancient environments, including cases that resemble mechanical or manufactured forms. Fossils are not just remains of organisms. They are records of interaction, pressure, motion, and contact preserved in sediment before it hardened into rock. In most cases, these records are biological: footprints, burrows, feeding marks. But occasionally, structures are found that do not align cleanly with known biological patterns. These are not objects, they are imprints. And in some cases, they resemble forms associated with tools, footwear, or mechanical interaction. One of the most debated examples involves a fossilized imprint discovered in sedimentary rock layers dated hundreds of millions of years old. The structure appears as a flattened, elongated depression with a defined outline resembling the shape of a human shoe sole. The proportions, length, width, and curvature match modern footwear patterns with notable accuracy. Even more unusual is the context. Beneath the imprint, within the same layer, lies a compressed trilobite fossil. Trilobites are marine arthropods that went extinct approximately 260 million years ago. The positioning suggests that the organism was present in soft sediment when the imprint was made, and was subsequently crushed under pressure. From a purely observational standpoint, this indicates sequence: soft sediment to imprint to fossilization, which implies that whatever created the imprint interacted directly with the environment at that time. The standard explanation for such formations is pareidolia, the human tendency to recognize familiar patterns in random structures. Geological processes such as spalling, where layers of rock fracture under stress, can create shapes that resemble footprints or artificial outlines. And this explanation is valid in many cases. Rock fractures can produce curved edges. Layer separation can create flat depressions. Weathering can enhance contrast between regions. But the difficulty arises when multiple features align simultaneously. Proportional symmetry, defined heel and toe regions, consistent edge depth, interaction with underlying fossil material. Each feature alone can be random. Together, they begin to resemble structured imprinting. Another category of anomalous imprints involves linear and parallel grooves found in ancient rock formations. In several documented cases, these grooves extend across surfaces with consistent spacing, often measured in exact intervals, and maintain straight trajectories over distances of several meters. In engineering terms, parallel grooves with fixed spacing are typical of cutting or machining processes. In geology, grooves can form through erosion, glacial movement, or sediment displacement. However, natural grooves usually vary in depth, spacing, and direction due to irregular forces. Maintaining uniform spacing over long distances requires consistent force application, something not typically associated with natural erosion. In some formations, these grooves intersect at near-perfect right angles. Right angles are not impossible in nature, but they are statistically rare, especially when repeated across multiple structures. Another subset of fossil anomalies includes cylindrical depressions and puncture-like marks found in hardened sediment layers. These features resemble insertion points, as if objects were pressed or driven into soft material before lithification. In modern contexts, similar patterns are created by tools, rods, or mechanical components. Geologically, such formations can result from root systems, gas escape structures, or biological activity. But again, interpretation depends on pattern consistency. Natural processes produce variability. Structured systems produce repetition. The challenge is distinguishing between the two when preservation is incomplete. Now consider scale. If a technological entity, whatever its biological form, interacted with soft sediment, moved across surfaces, or applied force to materials, it would leave traces similar to those created by animals. But those traces would not necessarily be recognized as technological. They would be catalogued as unusual fossil formations, Because classification systems are based on known biological behaviors. Anything outside that framework is interpreted within it. This creates a systematic bias in interpretation, not intentional, but structural. We do not classify unknown imprints as technological because we do not expect technology to exist in those layers, which means potential evidence is filtered before it is analyzed. However, it is critical to maintain methodological discipline. None of these imprints provide definitive proof of artificial activity. Each can be explained individually through known geological or biological processes. But, as with previous categories, the issue is accumulation. When multiple independent features appear, geometric consistency, interaction with fossilized organisms, repeated patterns across locations, structural alignment beyond random distribution, the probability of purely coincidental formation decreases, not to zero, but to a level that justifies further investigation. And yet, most of these cases remain unresolved, not confirmed, not fully explained. They exist in a category often described as anomalous but inconclusive, which in scientific terms means they are documented but not integrated into the broader model. In the next part, we move deeper into physical evidence, objects embedded within coal and ancient sediment layers that display clear signs of metallurgy, shaping, and functional design. Coal is one of the most time-locked geological materials on Earth. It forms from dense accumulations of plant matter, compressed, heated, and chemically transformed over tens to hundreds of millions of years. Most major coal deposits date back to the Carboniferous period, roughly 300 million years ago. This creates a critical condition. Anything fully embedded inside solid coal must have been present before or during its formation, not after. Because once coal solidifies, it becomes a dense, compact structure with no natural pathways for large objects to penetrate without fracturing it. And yet, multiple reports over the last 2 centuries describe objects found inside coal blocks that show clear signs of manufacturing. One of the earliest documented cases dates to the late 19th century. During routine coal processing, a worker split open a large piece and reportedly discovered a metallic chain fully enclosed within it. The chain displayed uniform links, consistent shaping, and a pattern typical of crafted metalwork. The key detail was not the object itself, but its position. It was not attached to the surface. It was not lodged in a crack. It was embedded within the coal matrix. When the block split, the chain was revealed across both halves, indicating it had been inside the coal prior to the fracture. From a materials perspective, this raises immediate questions. Coal formation requires pressure, heat, and time. Any object present during this process would be subjected to mechanical compression and chemical alteration. If the chain was introduced later, there should be evidence of intrusion, fractures, displacement, or contamination pathways. In many such reports, these indicators are absent. Another case involves a metallic vessel, described as a small pot, found inside a coal seam during mining operations. The object displayed clear features associated with casting, defined edges, symmetrical structure, and a handle. Metallurgical analysis in reported cases indicated compositions involving iron alloys with non-random elemental distribution. This is significant. Natural metal deposits do not form as finished objects. They occur as ores, mixed with surrounding minerals, and require extraction and refinement. Shaped metal objects require melting, molding, or machining. All of these processes require controlled energy input, In another documented instance, miners reportedly uncovered a gear-like structure embedded within coal. The object featured evenly spaced teeth, symmetrical radial geometry, and a consistent diameter. In mechanical systems, gear teeth are not arbitrary. They require precise spacing to function. Even small deviations disrupt motion transfer. The presence of such geometry implies design constraints. Natural geological processes can produce radial patterns, such as crystal growth or nodular formations. But producing evenly spaced, functional tooth-like structures with uniform geometry is statistically unlikely without guided formation. Now, consider the environmental constraints. Coal seams are formed from plant matter accumulated in swamp-like conditions. Over time, layers of sediment bury this material, increasing pressure and temperature. During this process, organic material is compacted, gases are released, chemical bonds are altered. Any embedded object would be exposed to these conditions for millions of years, which leads to a paradox. If the objects are modern contaminants, they should not appear structurally integrated into solid coal without visible intrusion. If they are ancient, they must have survived extreme geological processes while retaining identifiable structure. Both scenarios present problems. The standard explanation again returns to contamination. Objects may fall into coal during storage or transport, later appearing embedded. Or they may be forced into cracks during mining operations. But these explanations depend on the presence of fractures or weak points. In cases where objects are found fully enclosed within intact coal blocks, the contamination hypothesis becomes less stable. Still, no single case provides definitive proof. Documentation is often incomplete. Chain of custody is unclear. Many findings rely on eyewitness reports rather than controlled scientific analysis. This limits their evidential value. However, the pattern persists across multiple locations and time periods. Different countries, different geological contexts, similar types of objects. Chains, vessels, rods, gear-like forms. Each case is individually questionable. But collectively, they suggest a recurring anomaly. And this is where scientific caution intersects with uncertainty. Because the correct response is not to accept these objects as evidence of ancient civilization, but also not to dismiss them without analysis. They represent data points that do not fully align with expected geological processes. And unresolved data points, especially when repeated, indicate gaps in understanding. Whether those gaps are due to misinterpretation, unknown natural processes, or something more complex remains open. In the next part, we shift from visible objects to microscopic evidence. Structures measured in micrometers that resemble engineered components, potentially pointing to a level of material manipulation far beyond what conventional models allow. When we shift from large artifacts to microscopic structures, the nature of the evidence changes completely. At the macro scale, ambiguity dominates. Shapes can be misinterpreted. Context is often unclear. But at the micro scale, measured in micrometers, geometry becomes far less forgiving. Because at that level, structure is controlled by physics at the atomic and crystalline level, and deviations from natural growth patterns become easier to detect. One of the most discussed findings in this category comes from the Ural Mountains, where researchers identified microscopic spiral structures embedded in sediment layers dated to hundreds of thousands of years. These structures are extremely small, some measuring just a few micrometers in length. But their geometry is precise. They exhibit consistent helical turns, uniform pitch, proportional scaling, symmetry, along the central axis. In engineering, these are characteristics of manufactured coils or micro-components. In nature, spiral structures do exist at both macro and micro scales. Shells, DNA, and certain mineral growth patterns all exhibit spiral geometry. But natural spirals typically follow logarithmic growth patterns and vary in consistency due to environmental fluctuations. These microstructures, however, maintain uniformity beyond what random growth usually produces. Material composition adds another layer. Analyses have reported the presence of metals such as tungsten, molybdenum, and copper within these structures. These elements have very high melting points and are rarely found combined in pure, structured forms in natural, sedimentary environments. More importantly, they require significant energy to process. Tungsten, for example, melts at over 3,400 degrees Celsius. This is not a temperature reached through standard geological sediment formation. Now, to be precise, high temperatures do occur in geological systems, during volcanic activity or deep crust processes. But those environments produce chaotic, irregular formations, not uniform microscale spirals with consistent geometry. This creates a contradiction. If the structures are natural, they represent an unknown formation mechanism. If they are artificial, they imply controlled material processing at microscales. And that leads to a second category, glass-like spheres. In deep ocean sediment cores, researchers have identified microscopic spheres composed primarily of silicon dioxide, essentially glass. These spheres are highly uniform in size, nearly perfectly spherical, optically clear, evenly distributed within specific sediment layers. In modern industry, similar spheres are used in optics and electronics. Their production requires controlled melting and rapid cooling processes. Natural analogs do exist, such as microtektites formed by meteorite impacts. However, impact-generated spheres typically show irregular distribution, variable composition, internal bubbles, or structural imperfections. The spheres in question display a level of uniformity that raises questions about formation conditions. Additionally, some exhibit surface patterns resembling diffraction structures, features associated with controlled optical manipulation. At this point, the standard explanations again rely on rare, natural processes. Unusual crystallization, extreme pressure conditions, localized heating events, and individually these explanations remain plausible. But as before, the issue is not a single anomaly. It is convergence. When multiple independent features appear together, precise geometry, high-temperature materials, uniformity across samples, structural resemblance to functional components, the probability space narrows. Another category involves crystalline formations with internal cavities. Certain quartz crystals have been found containing perfectly geometric voids, cubic or rectangular spaces with smooth, flat surfaces at near-perfect right angles. Inside some of these cavities, mineral deposits form patterns that resemble circuit-like arrangements. Now, quartz crystallization is well understood. It forms under specific temperature and pressure conditions, growing along defined lattice structures. But creating internal cavities with sharp angles and polished surfaces requires interruption or modification of growth conditions in a highly controlled way. Again, natural explanations exist, such as pseudomorphs or mineral replacement processes. But these typically preserve irregular forms, not precise geometric voids. At this level, interpretation becomes increasingly technical. We are no longer dealing with visible artifacts, but with material science. And here, one important limitation appears. Detection depends on expectation. Geologists are trained to identify natural mineral structures. Engineers are trained to identify manufactured components. When a structure sits at the boundary between these categories, classification becomes uncertain, and uncertainty leads to conservative interpretation. Which means most of these findings are categorized as rare geological phenomena. Not because they are fully explained, but because there is no accepted framework to classify them otherwise. This does not confirm artificial origin, but it highlights a gap between observation and explanation. And when such gaps repeat across independent data sets, they begin to form a pattern, not of proof, but of unresolved structure. In the next part, we move back to large-scale systems, subterranean structures that demonstrate engineering complexity at a level difficult to reconcile with known historical timelines. When discussions move from microscopic anomalies to large-scale structures, the level of complexity changes. At this scale, we are no longer dealing with interpretation of shapes. We are dealing with engineering constraints. Because large structures require planning, energy, and coordination. One of the most studied examples of subterranean systems is located in central Turkey, in the region known as Cappadocia. Beneath the surface lies a network of underground cities, multi-level complexes carved into volcanic rock, extending tens of meters below ground. The largest of these, Derinkuyu, reaches depths of approximately 80 to 85 meters and contains multiple interconnected levels. From an engineering perspective, several features stand out immediately. First, volume of material removed. Estimates suggest that millions of cubic meters of rock were excavated to create a single complex. This is not a small-scale excavation. It implies long-term planning, workforce organization, and a method for removing and disposing of material. Yet large external spoil deposits, expected from such excavation, are not clearly identified. Second, structural precision. Walls, ceilings, and passages show consistent geometry. Many corridors maintain uniform width and height over long distances. Some vertical shafts extend tens of meters with minimal deviation from a straight axis. Manual excavation with primitive tools typically produces irregular surfaces. Here, surfaces appear controlled. Third, ventilation systems. These underground cities include vertical shafts designed to circulate air across multiple levels. The airflow system is not random. It is structured. Fresh air is distributed throughout deep sections of the complex. Maintaining breathable conditions at such depths requires understanding of pressure differences and air movement. Without this, lower levels would become uninhabitable. Fourth, defensive mechanisms. Large, circular stone doors, sometimes weighing hundreds of kilograms, can be rolled into place to block passages. These doors are positioned at strategic choke points, suggesting deliberate design for controlled access. Fifth, internal infrastructure. Within these systems are spaces identified as storage areas, living quarters, water access points, and communal zones. The layout is not chaotic. It follows functional organization. Now, the accepted historical explanation attributes these structures to relatively recent human activity, primarily early communities expanding natural cave systems using basic tools over extended periods. This explanation is not without merit. Volcanic tuff, the rock type in Cappadocia, is relatively soft and can be carved manually. However, several inconsistencies remain. Scale is the first. Expanding natural caves into multi-level complexes of this size would require sustained effort over generations. This is possible, but would typically leave clearer evidence of progressive construction stages. Second, precision. Maintaining consistent geometry across deep vertical shafts and extended corridors using only manual tools requires extremely high skill and time investment. Third, system integration. Ventilation, access control, and spatial organization appear integrated from the start, not randomly added over time. This suggests planning at a system level, not just incremental expansion. And finally, distribution. There are not just one or two such complexes, but hundreds across the region, some interconnected by long tunnels extending kilometers. This implies not isolated construction, but a coordinated architectural tradition. Now, to remain precise, these structures are not dated to 200 million years ago. They are part of known human history, but they demonstrate something important. They show that large-scale underground engineering is possible, and that such systems can survive for long periods when protected from surface erosion. This introduces a key concept: subsurface preservation. Unlike surface structures, underground constructions are shielded from weathering, erosion, and many geological processes. This significantly increases their chances of survival over time. However, even subsurface structures are not immune. Tectonic activity can deform or destroy them. Sediment accumulation can bury them deeper. Heat and pressure can alter their structure. Over tens of millions of years, even underground systems would degrade. But compared to surface cities, their survival probability is higher. This leads to a question. If an ancient civilization existed and understood long-term survival constraints, would it build on the surface or below it? And if such structures existed 200 million years ago, what would remain of them today? Likely not open chambers or intact corridors, but possibly anomalous voids, unexplained tunnel-like formations, regions of altered rock geometry, subsurface anomalies detected indirectly. Modern detection methods, such as seismic imaging and ground-penetrating radar, are beginning to reveal underground structures at various scales. Most are natural, some are human-made, and a small number remain unexplained, not because they are necessarily artificial, but because their formation does not fully align with known processes. Once again, we arrive at the same pattern. Not proof, but deviation. And when deviations repeat across different scales, microscopic, material, structural, they begin to form a consistent question. Not, is this evidence, but why do these anomalies exist at all? In the next part, we move into one of the most measurable categories of evidence: chemical and isotopic signatures preserved in rock layers, which may indicate processes involving energy levels far beyond typical natural systems. At geological timescales, the most persistent evidence is not structural. It is chemical. More specifically, isotopic. Because while physical objects degrade, isotopic ratios can remain detectable long after their original source has disappeared. Every natural process leaves a signature. Volcanic eruptions alter sulfur isotopes. Biological activity affects carbon ratios. Ocean chemistry shifts oxygen isotopes. These signatures are measurable, repeatable, and form the foundation of geochemistry. Now consider technological processes. They also leave signatures, but of a different kind. High-energy reactions, especially nuclear, produce isotopes that are either extremely rare or behave in ways that are difficult to replicate through natural mechanisms. One of the most discussed anomalies involves the detection of carbon-14 in geological layers that are tens of millions of years old. Carbon-14 has a half-life of approximately 5,730 years. This means that after about 50,000 years, it becomes virtually undetectable. After millions of years, it should be completely absent. And yet, in some deep sediment samples, trace amounts have been reported. From a strict scientific perspective, the first explanation is contamination. Modern carbon entering ancient samples during extraction or analysis. And in many cases, this is the correct explanation. But in certain data sets, contamination pathways are not clearly identified, and the anomaly appears across multiple samples. This does not confirm ancient activity, but it introduces uncertainty in interpretation. A second category involves heavier elements, such as plutonium isotopes. Plutonium-244 has a half-life of about 80 million years. It can exist naturally, but only in extremely low concentrations, typically formed through rare astrophysical processes or spontaneous nuclear decay chains. In some Triassic-era formations, elevated concentrations of plutonium isotopes have been reported, higher than expected background levels. More importantly, the ratio between different plutonium isotopes does not always match natural formation models. In controlled nuclear systems, isotope ratios are altered through neutron capture processes. This creates patterns that differ from natural decay. If such patterns are observed in ancient rock, they require explanation. Natural hypotheses include unusual uranium deposits, localized natural reactor conditions, cosmic radiation events, all of which are possible. But each requires very specific conditions, and when anomalies appear outside those conditions, explanation becomes less direct. Another class of evidence involves isotopic shifts associated with rapid climate change events. For example, sudden increases in carbon dioxide levels can be traced through changes in carbon isotope ratios. One of the most well-known events, the Paleocene-Eocene thermal maximum, shows a rapid shift in carbon isotopes consistent with massive carbon release. The cause is still debated. Methane release from ocean sediments is one explanation. Volcanic activity is another. But the key point is this: the isotopic signal exists. The cause is inferred. Now imagine a similar signal, but without a clear natural driver. If a technological system released large quantities of carbon into the atmosphere through combustion or industrial processes, it would produce a similar isotopic shift. But without context, it would be interpreted as a natural event, because that is the default assumption. This leads to a fundamental limitation. Geochemistry can detect change, but it cannot always identify the source of that change, especially when multiple processes can produce overlapping signals. Another indicator involves synthetic isotopes, elements or isotopic combinations that do not occur naturally in stable environments. Certain isotopes are only produced through nuclear reactions. If found in ancient contexts, they could suggest high-energy processes. However, detection at such timescales is extremely difficult. Radioactive decay reduces signal strength. Geological recycling redistributes material. Oceanic crust, where many chemical records are stored, is continuously subducted and destroyed. Less than 1% of ocean floor older than 200 million years still exists, which means most chemical evidence from that period is gone, even if it once existed. This reinforces a key conclusion. The absence of isotopic evidence does not confirm absence of activity. It may reflect loss of record. At the same time, the presence of anomalies does not confirm artificial origin. It indicates deviation, and deviation requires explanation. When multiple independent isotopic anomalies appear, unexpected isotope ratios, elevated concentrations beyond background levels. Combinations not predicted by natural models, they form a signal. Not definitive, but measurable. And unlike physical artifacts, isotopic data can be tested, replicated, and quantified, which makes this category of evidence the most scientifically robust and the most difficult to interpret conclusively, because it exists at the boundary between natural and artificial processes. In the final part, we bring all categories together: environmental conditions, preservation limits, material anomalies, structural systems, and chemical signatures, to answer the central question, not whether a civilization existed, but whether current science is capable of ruling it out. We now have the full structure of the problem, not assumptions, not speculation. A layered model built from 5 independent domains: environmental conditions, geological preservation limits, material anomalies, structural systems, isotopic signatures. Each of these domains on its own does not prove the existence of a pre-human technological civilization, but none of them eliminate the possibility either. And this is where the conclusion must be precise. First, conditions. The Earth 200 million years ago was not hostile to complexity. It was stable, resource-rich, and globally connected through Pangea. From a systems perspective, it allowed for large-scale biological development. Second, time. The Triassic period lasted tens of millions of years, enough for multiple evolutionary experiments, including intelligence, to emerge, even briefly. Third, preservation. Geology does not store surface history effectively. Over hundreds of millions of years, nearly all direct evidence, cities, tools, infrastructure, would be destroyed, transformed, or rendered unrecognizable. This is not a hypothesis. It is a constraint. Fourth, anomalies. Across independent datasets, we observe metallic structures in ancient rock, embedded objects in coal formations, imprints that do not fully match known biological patterns, microstructures with engineered geometry, subterranean systems with unexplained features, isotopic deviations beyond expected models. Each anomaly has a possible natural explanation, but the explanations are often case-specific, isolated, and do not scale across all observations. Fifth, methodology. Modern science relies on models built from available data, but those models are constrained by a critical limitation. We only have one confirmed example of technological civilization: ours. This creates a circular framework. We define what is possible based on a single data point, and then we evaluate all evidence against that definition. Anything outside it is classified as anomaly, not because it is false, but because it does not fit. This is not a flaw. It is how scientific models maintain consistency, but it creates blind zones. Now we return to the central question. Not, did a civilization exist 200 million years ago? There is no definitive evidence to confirm that, but also not that it is impossible, because based on current knowledge, that statement cannot be supported either. The correct scientific position is narrower and more precise. We do not have sufficient evidence to confirm the existence of a pre-human technological civilization, but we also do not have sufficient evidence to conclusively rule it out. And that distinction matters, because it defines the boundary between knowledge and assumption. Now consider the implication. If even a small fraction of the anomalies we discussed are misclassified, if they represent processes not yet understood or recognized, then our reconstruction of Earth's history is incomplete. Not wrong, but incomplete. And that is expected, because we are working with a fragmented record, reconstructed from less than 1% of the original data. Most of Earth's history is missing, recycled, compressed, erased, which means our conclusions are based not on the full dataset, but on what survived. And survival in geology is not representative, it is selective. So the final answer is not a statement, it is a boundary condition. At our current level of scientific resolution, the existence of an advanced civilization 200 million years ago remains unproven. But it is not excluded, and until it is excluded or confirmed, the anomalies remain, not as evidence of a hidden history, but as signals that our understanding is still incomplete, which leaves one final question. Not about the past, but about the present. If a civilization could rise, transform a planet, and disappear almost completely within geological time, what traces of our own civilization will remain 200 million years from now?